Astronomers pointed the James Webb Space Telescope at a small, unremarkable patch of sky and found something that, according to their own published research, simply wasn't supposed to exist at that point in cosmic history. Not one galaxy, not two, but 5 separate galaxies, actively colliding and merging together, wrapped in a glowing halo of gas that shouldn't have been there at all, existing at a point when the universe was less than 1 billion years old. The lead researcher behind the discovery said, "What makes it so remarkable is that nobody expected a merger involving this many galaxies to happen this early. This is the real story of what researchers are now calling JWST's quintet, why 5 galaxies colliding at once broke a specific assumption astronomers had relied on for years, and what it reveals about heavy elements being scattered into space far earlier than anyone thought possible. If you want real discoveries explained accurately instead of exaggeration, subscribe now, because this specific result is forcing astronomers to rebuild part of their own model of how galaxies actually grow." Let's start with what astronomers actually expected to find when they look this far back into cosmic history, because understanding the specific prediction that got broken here is the whole key to this story. Looking at objects billions of light years away means looking at light that's been traveling for billions of years to reach us, meaning the deeper into space a telescope looks, the further back in time it's actually seeing. The system at the center of this story sits at a redshift of 6.71, corresponding to roughly 800 million years after the Big Bang, an extraordinarily early point in the universe's 13.8 billion year history. At that specific stage, the standard model of galaxy formation predicted galaxies should still be relatively small, relatively isolated, and only just beginning to interact with each other in simple, limited ways. When mergers did happen this early, models generally expected them to involve at most 2 or 3 galaxies colliding at once, a comparatively modest, easily explained kind of interaction consistent with a universe still in its early, sparse stages of building larger structures. A research team led by Wei Hu, a postdoctoral researcher at Texas A&M University, working alongside Casey Popovich, a professor of physics and astronomy at the same institution, found something that broke that specific prediction directly. Using data gathered through the JWST Advanced Deep Extragalactic Survey, one of the deepest, most detailed imaging campaigns ever conducted using the James Webb Space Telescope, the team identified a system they nicknamed JWST's Quintet, a genuinely rare, tightly packed collision involving at least 5 separate galaxies, all interacting simultaneously within a single, compact region of space, at a point in cosmic history when astronomers had generally expected to find nothing more complex than an isolated pair. If a story built on real, peer-reviewed research published in Nature Astronomy is the kind of thing you want more of, drop a like on this video right now. It genuinely helps this content reach more people who'd get value out of it. Hu described exactly why this specific number matters so much in the statement accompanying the published research, explaining directly that what makes the discovery remarkable is that a merger involving this many galaxies simply wasn't expected this early in the universe's history. At a point when galaxy mergers were generally thought to be simpler affairs, usually involving only 2 or 3 galaxies at most. 5 is a genuinely different category of event entirely, and finding it this early in cosmic history represents exactly the kind of result that forces researchers to seriously reconsider assumptions that had otherwise gone largely unchallenged. If you found this specific broken prediction as fascinating as I did while researching it, drop a comment and let me know. It genuinely helps me figure out what to cover next. It helps to understand what actually makes a galaxy qualify as an emission line galaxy in the first place, since that's the specific classification underlying the ELG1 through ELG5 labels the research team gave each individual member of the system. Rather than emitting a smooth, continuous spread of light across the entire visible spectrum the way an ordinary star does, an emission line galaxy shows bright, distinct spikes of light at very specific wavelengths, produced when hot, ionized gas within the galaxy, heated by intense radiation from newly formed, massive young stars, emits light at precise, well-understood wavelengths tied directly to the specific chemical elements present. Detecting those distinct spikes is exactly how astronomers were able to identify individual oxygen and hydrogen emission within this system in the first place, since each element produces its own characteristic pattern of emission lines that shows up as a recognizable signature within Webb's detailed spectroscopic data. Galaxies that show this kind of bright, distinct emission line pattern are also generally excellent tracers of intense, ongoing star formation, which is precisely why finding 5 of them clustered together, all producing stars at such an extraordinary combined rate, immediately signaled to researchers that this specific system deserved considerably closer examination. It's worth understanding the actual physical layout of this system, because the specific combination of characteristics involved is what makes it so genuinely unusual. The 5 individual galaxies making up JWST's quintet, labeled ELG1 through ELG5 in the team's published research, referring to emission line galaxies, sit separated from each other by tens of thousands of light years, a genuinely enormous distance by any everyday standard, but remarkably compact when measured against the sheer scale of the observable universe as a whole. Despite that separation, the 5 galaxies occupy an unusually tight, compact overall region of space for a system this early in cosmic history, and every one of them was found to be forming new stars at an extraordinary pace, with the entire system collectively producing new stars at a rate equivalent to roughly 250 times the mass of our own sun every single year, a pace considerably higher than what astronomers typically find in galaxies existing at the same general point in cosmic time. Here's where the discovery gets genuinely more significant than simply finding an unusually large merger, because the research team didn't stop at counting galaxies. They also detected something extending well beyond the boundaries of the 5 individual galaxies themselves, an extended halo of glowing gas, linking several of the colliding galaxies together, emitting light specifically associated with ionized oxygen and hydrogen. That detail matters enormously, and it's worth taking a moment to understand exactly why, because oxygen isn't a raw ingredient the universe started out with in any meaningful quantity. Elements heavier than hydrogen and helium, what astronomers generally refer to as metals, regardless of whether they're metals in the everyday sense, have to be forged inside stars through nuclear fusion and then released into the surrounding environment when those stars eventually die, whether through a gradual process of stellar winds or a sudden, violent supernova explosion. Finding a genuine halo of oxygen-enriched gas sitting outside the actual galaxies themselves means researchers were looking directly at material that had already been through at least one full cycle of star formation and stellar death, then physically removed from its home galaxy and scattered into the surrounding environment, all happening at a point in cosmic history less than 1 billion years after the universe itself began. If you found this connection between galactic collisions and scattered heavy elements as interesting as I did, drop a comment and let me know. It genuinely helps me figure out what to cover next. The research team specifically investigated what physical process was actually responsible for pushing that oxygen-rich gas out beyond the individual galaxies in the first place, because there were 2 genuinely different explanations worth distinguishing between. One possibility involved galactic winds, powerful outflows of gas driven outward by intense radiation and stellar explosions happening within each individual galaxy, a process that can push enriched material outward even without any external collision involved at all. The second possibility involved the gravitational interactions of the merger itself, material getting physically stripped and flung outward as the 5 galaxies' mutual gravity pulled and distorted each other during the actual collision process. According to the team's published analysis, the evidence pointed primarily toward that second explanation, the gravitational dynamics of the merger itself, rather than galactic winds alone, as the dominant mechanism responsible for scattering this enriched gas into the surrounding space. That's a genuinely important distinction, because it provides direct observational evidence that galaxy collisions themselves, not simply the individual galaxies acting independently, were already actively reshaping the chemical makeup of their surrounding cosmic environment far earlier than existing models had accounted for. Casey Popovich addressed the broader significance of this finding directly, framing it within a larger pattern of tension that's been building across the field of early universe astronomy since Webb first became operational. He explained that this discovery helps account for a growing mismatch between what astronomers' existing models predict and what Webb is actually observing directly, and stated plainly that by demonstrating a complex merger-driven system exists this early, the discovery indicates that researchers' theories of how galaxies actually assemble and how quickly they're capable of doing so need genuine updating to match what the telescope is actually finding. That framing matters because JWST's quintet doesn't exist as an isolated anomaly, sitting apart from everything else Webb has found in the early universe. It connects directly to a much broader ongoing pattern that's shown up repeatedly since Webb began operations, individual galaxies appearing more massive and more chemically developed than expected this early in cosmic history, unusually large protoclusters of galaxies assembling faster than models predicted. And now, with this specific discovery, an unusually complex 5-galaxy merger actively redistributing heavy elements at a point when astronomers expected nothing more than simple, isolated pairs of colliding galaxies at most. It's worth digging a bit deeper into exactly how researchers went about distinguishing between those 2 competing explanations for the scattered oxygen gas, galactic winds versus gravitational stripping during the merger, because that distinction required genuinely careful analytical work rather than a simple, obvious visual confirmation. Galactic winds tend to produce a fairly specific, recognizable pattern, gas driven outward roughly symmetrically from a single galaxy's center. following pathways shaped by that galaxy's own internal structure and the direction its most intense star formation happens to be concentrated. Gravitationally stripped material, by contrast, tends to follow considerably messier, more asymmetric pathways, stretched out along the specific directions where the mutual gravitational pull between colliding galaxies is actively distorting and pulling matter away from each one. By carefully mapping the actual distribution and motion of the oxygen-enriched gas detected throughout this system, and comparing that distribution against the specific positions and orbital paths of the 5 individual galaxies involved, Hu's team was able to build a case that the observed pattern matched the messier, gravitationally driven signature considerably better than it matched what a collection of independent galactic winds would typically be expected to produce, giving their conclusion a genuine, evidence-based foundation rather than simply defaulting to the more dramatic-sounding explanation. It's worth understanding why the research team chose the specific nickname JWST's Quintet for the system, because the name is a deliberate callback to one of astronomy's more famous galaxy groupings. Stephan's Quintet, a group of 5 galaxies located roughly 290 million light-years from Earth, has been a favorite target for astronomers and astrophotographers for well over a century, and became one of Webb's own most celebrated early images after its 2022 debut, showing the dramatic, tidally distorted shapes of galaxies caught in the act of gravitational interaction. But Stephan's Quintet sits enormously closer to Earth, and enormously later in cosmic history than the system covered throughout this video. The new discovery, sitting at a redshift of 6.71, existed when the universe was less than 1 billion years old, compared to Stephan's Quintet's considerably more recent nearby interaction. Borrowing that familiar name for this newly discovered system is a deliberate way of signaling the parallel. A genuine multi-galaxy collision, just one occurring at a point in cosmic history dramatically earlier than anything resembling it that astronomers had previously documented in this kind of detail. It's worth acknowledging the full research team behind this discovery too, because a result this detailed rarely comes from just 2 names on a paper. Alongside Hu and Popovich, the published research credited additional Texas A&M contributors, including Lu Shen, a postdoctoral research associate, Justin Spilker, an assistant professor, and Justin Cole, a doctoral student, reflecting the kind of multi-person collaboration typically required to properly analyze a dataset this complex, spanning everything from precise galaxy identification to detailed chemical mapping of the surrounding gas halo. The research was supported by funding from the National Science Foundation, NASA, the Kavli Institute for Theoretical Physics, and additional private support, a combination reflecting how modern astrophysics research generally depends on multiple overlapping sources of funding working together to support the kind of sustained detailed analysis a discovery like this one actually requires, from the initial deep survey observations all the way through to the final, published interpretation of what that data actually revealed. There's a specific forward-looking implication tied to this discovery too, one connecting it directly to a separate mystery Webb has been grappling with elsewhere in its own observations. Researchers studying the early universe have also identified a growing number of massive galaxies that appear largely inactive, essentially finished with their major star-forming activity, sitting at points in cosmic history just a few billion years after these earliest mergers would have occurred. Popovich's team has proposed a genuinely compelling connection between those 2 separate findings, suggesting that systems like JWST's Quintet, if they merge rapidly and burn through their available star-forming gas quickly during that merger process, could represent exactly the kind of early formation event that eventually produces those later, massive, inactive galaxies. Astronomers have already been puzzling over separately. In other words, this single discovery may not just explain one anomaly on its own, but potentially help connect 2 previously separate, seemingly unrelated mysteries that had already been challenging existing models of galaxy evolution. It's worth situating this discovery within the broader ongoing tension that's been building across early universe astronomy since Webb first became fully operational, because JWST's Quintet represents one more addition to a pattern that's been steadily accumulating. Since 2022, researchers using Webb have repeatedly identified individual galaxies that appear far more massive, far more chemically developed, and far more structurally mature than the standard model of cosmology, often called lambda CDM, predicted should be possible at their specific point in cosmic history. Some of those discoveries involved single, unusually bright galaxies. Others involved entire populations of compact, mysterious objects nicknamed little red dots, several of which turned out to be actively feeding black holes carrying masses that don't comfortably fit existing models of how black holes are supposed to grow this early. Still others involved massive, gravitationally bound clusters of dozens of galaxies, already assembled at a point when current theory says building a structure that size should have taken considerably longer. JWST's Quintet adds an entirely distinct category of evidence to that same growing pile, not simply an unusually massive individual object, but direct proof that complex multi-galaxy interactions and the chemical enrichment those interactions actively produce were already well underway, far earlier than the standard model of galaxy assembly had ever predicted. It's worth being clear about exactly what comes next for this specific research, because the team hasn't treated this discovery as a finished, closed case. According to the published research, future Webb observations are already planned specifically to examine the motion of both the gas and the individual galaxies within this exact system in considerably more detail, aiming to build a more complete, dynamic picture of exactly how this merger is actually unfolding over time, rather than relying purely on the single snapshot captured so far. That kind of planned follow-up reflects a genuinely careful, methodical approach to a discovery this significant, treating the initial detection as a starting point for deeper investigation, rather than a single, standalone headline moment. It's also worth appreciating the sheer technical achievement required to make a discovery like this possible in the first place, because identifying 5 separate, actively interacting galaxies at this specific distance required extraordinary sensitivity. The JWST Advanced Deep Extragalactic Survey that originally captured this system represents one of the deepest imaging campaigns ever conducted with Webb's instruments, requiring extremely long cumulative exposure times specifically to gather enough light from objects this faint and this distant to actually resolve meaningful detail, distinguishing 5 separate galaxies, rather than simply registering a single blurred point of light, and then further identifying the specific chemical signature of oxygen-enriched gas extending between them, represents exactly the kind of fine-grained observational capability that simply didn't exist before Webb became operational, which is a significant part of why this specific category of discovery, unusually complex, chemically detailed early universe systems, has only started emerging in the research literature since Webb began its own science operations back in 2022. It's worth adding one final piece of technical context, because the redshift measurement anchoring this entire story, 6.71, isn't a casual estimate either. Determining a galaxy's precise redshift, and therefore its precise distance and age, requires identifying specific, recognizable spectral features within its light, and measuring exactly how much those features have shifted toward longer, redder wavelengths due to the ongoing expansion of the universe since that light was originally emitted. The same emission line signatures that allowed researchers to classify these 5 galaxies and detect their surrounding oxygen halo also provided the precise spectral fingerprints needed to calculate that redshift value with real confidence, tying the entire discovery. The galaxy count, the merger dynamics, the chemical enrichment, and the exact point in cosmic history, all of it occurred back to the same underlying spectroscopic dataset gathered by Webb's instruments. So, what does all of this actually add up to? Using data from one of the deepest surveys ever conducted with the James Webb Space Telescope, researchers identified a genuinely unexpected system, 5 separate galaxies actively colliding and merging together at a point in cosmic history only 800 million years after the Big Bang, considerably earlier, considerably more complex than existing models, predicted a merger of this scale should be able to occur. Beyond the sheer number of galaxies involved, the system revealed direct observational evidence that this specific collision was actively scattering oxygen-enriched gas, material forged inside stars and released through their eventual deaths, into the surrounding space well outside the boundaries of the individual galaxies themselves, primarily driven by the gravitational dynamics of the merger, rather than galactic winds alone. There's a genuinely satisfying quality to how this specific discovery actually came together, one worth appreciating before wrapping up. It didn't require a single dramatic observation or a lucky coincidence. It came from systematically working through one of Webb's deepest, most patient survey programs, the kind of methodical, unglamorous data gathering that rarely generates headlines on its own, until a genuinely unusual pattern emerged clearly enough for researchers to recognize it as something worth a dedicated, focused study. That's precisely the kind of foundation solid, lasting scientific claims are actually built on, and it's exactly why Popovich's own framing of the result, that existing theories of galaxy assembly need genuine updating to match what Webb keeps finding, carries the kind of weight it does within the broader astronomical community. If stories like this, grounded entirely in real published research instead of exaggerated headlines, are what you come here for, subscribe to this channel and turn on notifications, because Webb is still actively searching the earliest reaches of the observable universe, and there's a very real chance the next discovery adds even more detail to exactly this story. Thanks for watching, and I'll see you in the next one.